Hello, everybody. My name is Abdulazim Sayed, and my CWID is 5035687 Uh, my topic for today is driver drowsiness detection based on convolution neural network architecture and optimization using genetic algorithm. Let's quickly head towards the content. So our today's agenda would be introduction and then going towards the problem statement and giving a review of objectives and then the literature review and methodology section has block diagram, UML diagrams, algorithm, then the setup, and then finally the results and discussion with a closing with conclusions and scope. So let's go toward the introduction and get a brief of what kind of project is this. So for the safety critical needs, drowsy driver causes thousands of accidents annually. Real-time detection can saves lives by warning drivers before they doze off. And detection challenges would be like drowsiness detection is difficult due to lighting changes, facial occlusions, and glasses or head turns, and then the need for real-time performance. The proposed system is that, my approach basically combines an autoencoder for early anomaly detection and in facial behavior. And then it contains MobileNet and lightweight CNN for fast and accurate classification. So this is a hybrid model that delivers high accuracy with low computational idle for uh, real use. Uh, and yeah, our key advantages are, the system is practical and deployable, runs efficiently on embedded devices and mobile devices, adapts to real world conditions, whether it is day or night, and with or without glasses, with or without masks. That depends. So it also supports multi-sensor input, making it flexible across vehicle types. And then I would say its impact could be like, this is scalable solution enables real-time alerts to reduce accident risks. And then whether in autonomous or human-driven vehicles, it promotes safer roads and smarter transport systems. For the problem statements, let's take a look at the features. So real-time driver monitoring. So it has real-time driver monitoring. So our goal is to basically, accurately detect the drowsiness and distraction in real time, despite the drowsiness and, despite the I'm sorry, my bad. So, despite the challenges in lighting changes, facial inclusions, and sudden behavior shifts, uh, and providing this all with high reliability. And then the lightweight and efficient, it is lightweight and efficient because we use autoencoders for anomaly detection and a mobile net for facial analysis. Both are lightweight and run smoothly with mobile and embedded hardware. And then it's a robust performance to ensure the adaptability. We apply self supervised learning, improve generalization, and then varying conditions and reducing the need of large data sets. So multi-sensor fusion is like basically, by combining the visual data with psychological motion sensors, and we enhance detection accuracy and overcome the limits of vision only systems. And then obviously it is a deployable solution because this system delivers the real-time alerts and is ready for deployment in autonomous and human-driven vehicles, contributing to safer and smarter roads. So the objectives would, the data sets and model training. So I have used a public Mendeley data set labeled driver states like alert, yawning, and sleep. So a mobile net based model was selected for its efficiency on embedded and mobile devices and trained using standard metrics, accuracy, precision, and recall to validate the performance. The real-time video analysis is like, our system analyzes live video frame by frame, classifying the driver's state as normal, fatigued, yawning, or asleep. It maintains high accuracy, speed, and is robust to lighting changes and camera angles, making it, actually reliable for the real world conditions. The hybrid sensor fusion is basically, to enhance the reliability. Uh, I have fused the visual data with psychological signals like ECG and heart rate variability. Autoencoders, detected the subtle anomalies in these signals, such as irregular heart rate or sudden movement, or enabling the earlier and more accurate fatigue detection. So it has been really helpful for me. This is the literature review, you know, uh, from the various people. So the first one is like, proposes a Kalman variation autoencoder model for anomaly detection and video frame production. The second one was like, it uses edge computing and crowdsourced data for drowsiness detection. And third one, focus on test methods for drowsiness and attention warnings. Uh, the fourth is introduces a multi-scale CNN for detecting drowsiness using facial features. And then next is reviews the radar-based system for in-vehicle monitoring. And then the introduces real-time facial detection for automotive safety systems. The other one is utilizes electrocardiogram or interval data for drowsiness detection. And then we go towards the methodologies. Give me 1 second. I'm sorry. Uh, the methodology, I would say that um, the hybrid model combines the mobile net for real-time visual analysis with autoencoders for psychological anomaly detection, addressing accuracy and noise sensitivity issues. For higher accuracy classification, it was trained on the Mendeley dataset to classify driver states such as normal, yawning, sleep, with optimized precision, obviously, to recall and frame level, frame level speed. And multimodal data fusion is like, it it fuses the video output with ECG and HRV data to capture subtle signs of fatigue, increasing reliability under collisions and lightning variations. And then the real-time deployment basically means that, it delivers low latency alerts with strong generalization across the diverse conditions, supporting effective on-the-road accidents prevention. And yeah, here is our block diagram. I would say uh, I don't want to take much of your time, so this is just the block diagram that I have it on the presentation. I won't be able to explain it much because it might consume a lot of time. And then this is our UML diagram, which clearly shows that driver is giving the input raw data to the detection system, and then it is detecting the fatigue, and then it is pre-processed data which alerts the system and generate an alert. So this is just a flow diagram, you could say, or UML diagram, which shows the process, the entire process of how the data is received and what kind of data is received and how it is processed using the mobile net and autoencoders for the image data and also the ECG data as well. The algorithm is like, the input features is input for the input, the facial images are annotated by LI, and psychological signals are by XI. So yeah, so output could be like fatigue or alert, and then the pre-processing of the images is resized to 220 by 224 with the normalized signals as well. And the models were like, model is like, the mobile net analyzes facial cues such as blinks. This is, autoencoder detects anomalies in ECG accelerometer data. And then, this is a hybrid approach and ensures the accurate real-time fatigue detection by combining visual and psychological insights. And the combined data is basically and denoted by L, which is L vision plus A of Lecron. This is the algorithm which has been used. Uh, let's go towards the setup. I'm really sorry for taking much of the time. And then this is the setup. The first feature is like, the data uses the Mendeley data set, which includes labeled visual and ECG signals collected under various lighting and weather conditions for robustness. And the model is a hybrid model combining mobile net for real-time facial analysis and autoencoder for detecting anomalies in ECG signals, which enables fatigue detection with low latency. The performance is evaluated for, the system is evaluated for accuracy, recall, and FPS, obviously under challenging conditions like low light and facial occlusions. So it compared with models like ADA boost and bagging for performance benchmarks. For the deployment, it is optimized for edge devices like Jetson, Raspberry Pi. The system supports multi-driver environments and sensor fusion from various vehicle sensors. The future improvements, I would say, it could include infrared imaging, head pose estimation, expanding the data set to improve accuracy and adaptability. So this is the phase one result, which has detected the on the left hand side is the input, and then on the right hand side it shows that the predicted one as yawning, and then true or not true as yawning, right? So true would be yawning if it is accurate. So that is all the data set. That is all the results from the provided data set. This is the confusion matrix of for the results. And then for the phase two, I've used my own real-time video results, which has and the accuracy was somewhere around 90 to 95%, around 90% obviously. And then this is the accuracy over epochs and the loss over epochs with a graph that I have shown. This is the phase three with ECG data, so which basically, tracks your heart rate and everything, which I've used for training purposes. And the tabulation was, the precision was like 0.9% for the bagging, random forest. And then for the logistic regression, it showed me like 0.82. And for the decision tree, it was 0.91 and as follows. So the conclusion I would say is like, the robust class balancing is like, the system enhances detection of underrepresented classes, example, yawning through data augmentation and class balancing, addressing the bias in data set and improving model fairness. The dual input hybrid architecture combines the CNN for visual features like facial cues and biometric data like ECG. The superior performance of the system is, it has achieved, as I said, 91 to 95, 92% accuracy, and in some cases it could go up to 95%. And then 0.99 recall on the yawn, surpassing traditional models like bagging and ADA boost. So this performance is crucial for detecting early signs of fatigue. And then the real-time reliability is optimized for real-time video analysis. You could use a camera or a webcam for, which ensures the low latency alerts in dynamic driving conditions by using an efficient layer design. And the scope, I would say, like, it has the enhanced robustness. The system will extend to low light infrared imaging in future and head pose estimation, improving the adaptability for real world deployment. So it will also incorporate vehicle sensor data, example steering and lane deviation as well. We have blind monitoring system, but it's a sensor. But then this would be connected with the camera inside your car as well to enhance the hybrid model accuracy. And then scalability and edge deployment is like, to improve generalization. The system will expand its training data to include diverse demographics and behaviors. So it will be optimized for embedded automotive systems, enabling continuous and real-time monitoring.
Okay, so let's start with our first file of the project. So this is the demo that I have. This is the file that I have executed. So the file imports essential libraries like TensorFlow, Keras, NumPy, OpenCV for model training and video analysis. We have used MobileNet to process facial images, ensuring fast and real-time analysis as well. And then we have an encoder which is used to extract features from psychological signs like heart rate and eye blinks. And the autoencoder detects anomalies indicating early signs of drowsiness when reconstruction is poor. So I have uh, ran the file, and it gave me the graphs and everything. And the facial and psychological features are basically combined to create a rich feature set for classification. And the classifier predicts the whether the driver is alert or early drowsy or drowsy. So this is the graphs which I got with the ECG reports and everything. And you see the pictures. These are my pictures, the live data set that I have used. You see, its prediction was sleepy, and then the decision was actually true. So true as sleepy. These are all the other conditions: sleepy, dehydration, normal, yawn, and dehydration and everything. These are all the data sets. These are all the data. And the classifier predicts whether the driver is alert or not. So it also includes the training, evaluation, and model saving for deployment. So this is the overview. Okay, so let's take a look at another file. So now the file displays the training and training versus validation accuracy, and also loss graphs to verify model performance. And let's it also shows the confusion matrices, helps us identify misclassification for model improvement. It includes the summarizing the model uh, mis- uh, architecture and layer details.
the construction error plots from the autoencoder when autoencoder show where the model struggles signaling early fatigue. So I have actually ran this file as well. Took a lot of time, but yeah, I'm sorry for taking much of your time. Let me just quickly go towards the output. So this is the output that I have got, and then these are the graphs which I have got after training the data, after training the model by giving all the data and everything. This is like, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a 10 layer model, the 10 layer as well. So, these charts basically demonstrates how combining facial and psychological features improves prediction. So, yes, you see the label distribution before feature extraction. That is the table that I have got. And then there it is, the balanced label distribution, the model. See, after all the execution, remember talking about the confusion matrix. This is the matrix that I have been given, like 800 pictures for dehydration, drowsy, 724, and then 585, 781. So these are the predictive labels. And that's all for the project. And thank you so much for staying with me.